Imagine a constant, invisible rain falling upon our planet. It's not water, it's not light, it is a relentless shower of tiny energetic particles. These particles are cosmic rays, they are atomic fragments, torn apart in the most violent events the universe has to offer. They travel across the vast emptiness of space for millions of years, sometimes billions of years. Most of them are moving at astonishing speeds, approaching the speed of light. They bombard the Earth from every direction, at every moment of every day. This silent, ceaseless downpour connects us to the distant, chaotic engines of the universe, from our own sun to galaxies far, far away. These travelers are not a form of light or radiation in the traditional sense, like X-rays or gamma rays. The name, coined by Robert Millikan in 1925, is a bit of a misnomer. They are physical matter, the nuclei of atoms, stripped of electrons and accelerated to incredible energies. When you stand outside, billions of these particles pass through your body, or the secondary particles they create, every minute. You don't feel them, you can't see them. Yet they are a fundamental component of our cosmic environment. In Ganshu Kosne Komposnabari, Dinobyron a ghostly testament to the universe's violence. They carry stories. It's our job as cosmic detectives to decipher them. The discovery of this invisible rain was a triumph of curiosity. In 1912, physicist Victor Hess took electroscopes up in a hot air balloon. He expected the radiation to decrease with altitude. To his astonishment, the opposite happened. The higher he went, the more intense the radiation became. He concluded it must be coming from above, outer space. So, what exactly are these cosmic rays made of? If you could catch them and put them under a cosmic microscope, you would find a familiar cast of characters from the world of particle physics. The overwhelming majority, about 90%, are the simplest atomic nuclei you can get. Single protons. Protons. These are the nuclei of hydrogen atoms, the most common element in the universe. It makes sense that they would be the most common component of this cosmic spray. They are the fundamental building blocks of stars and galaxies, and when things get energetic out there, protons are the first to be flung across space with incredible force. The next most common group, making up about 9% of the total, are alpha particles. Alpha particles. An alpha particle is simply the nucleus of a helium atom, consisting of 2 protons and 2 neutrons bound tightly together. Helium is the second most abundant element in the universe, forged in the Big Bang and in the hearts of stars. The remaining 1% is a fascinating zoo of other particles. This includes electrons, the same lightweight particles that power all of our electronics, and the nuclei of heavier elements carbon, oxygen, iron, uranium, term banner, composition, protons, alpha particles, electrons, trivia banner, uranium nuclei found. Finding the nuclei of heavy elements like iron or uranium is particularly exciting for astrophysicists. These elements are only created in the most extreme cosmic events, primarily the explosive deaths of massive stars known as supernovae. The fact that we can detect these heavy nuclei right here at Earth means we are directly sampling the ejected material from these cataclysmic stellar explosions. It's like a supernova sent us a package, and it only took a few million years to arrive. These heavy nuclei act as messengers, telling us about the chemical composition and the violent processes happening in the cosmic factories where they were born, providing crucial clues about the life and death of stars. Even more exotic is the tiny fraction of cosmic rays that are composed of antimatter. For every particle of matter, there exists an antiparticle with the same mass but opposite charge. Cosmic rays include positrons and antiprotons. The universe we see is overwhelmingly made of matter, so finding these bits of antimatter is a big deal. Are they created in high-energy collisions, like sparks flying from a cosmic anvil? Or do they come from more mysterious sources, perhaps even entire stars or galaxies made of antimatter? By studying these rare antiparticles, scientists hope to unravel one of the biggest mysteries in physics: why there is so much more matter than antimatter in the universe today. A primary cosmic ray, having traveled across the void for eons, finally ends its journey in the upper reaches of Earth's atmosphere, but its end is just the beginning of a new, dramatic event. When this high-speed particle, let's say a proton, slams into the nucleus of an oxygen atom or of a nitrogen atom about 10 to 15 kilometers above the ground, The collision is incredibly violent. The energy released is so immense that it shatters both particles and, through Einstein's famous equation E equals mc squared, creates a whole cascade of new, short-lived particles. This is the birth of an extensive air shower, a chain reaction that unfolds in a fraction of a second. This initial collision produces a spray of unstable particles, primarily pions, kaons. These particles are exotic and live for only a tiny fraction of a second before they decay. They are the immediate children of the original cosmic ray impact. They fly off in a cone shape, continuing downward and outward, carrying the energy of the initial collision with them. As these pions and kaons decay, they themselves transform into other particles, creating the next generation in the cascade. The air shower grows, spreading out as it plummets towards the ground, sometimes covering an area of several square kilometers. The most important decay products for us on the ground are muons. Muons are fundamental particles, much like electrons, but they're about 200 times heavier. This extra mass is key to their survival. Unlike many of the other particles in the shower, which are quickly absorbed by the atmosphere, muons are extraordinarily penetrative. They can travel through kilometers of air without being stopped. They are the hardy survivors of the atmospheric particle war, the last messengers of the initial cosmic ray collision. It is these muons, not the original primary cosmic rays, that make up most of the cosmic radiation that reaches the Earth's surface. So, when you hear that billions of cosmic rays pass through you every second, it's mostly these secondary muons that are being counted. They are raining down on us constantly. If you hold out your hand, about 1 muon passes through your palm every second. They stream through your body, through buildings, and even deep into the earth. Most of them are harmless, depositing only a tiny amount of energy as they pass. But their existence is direct proof of the cosmic ray bombardment happening high above our heads. Detecting these muons is one of the primary ways we study cosmic rays from the ground, using the atmosphere itself as a giant, natural particle detector. Tracing a cosmic ray back to its source is one of the greatest challenges in astrophysics. The universe is full of powerful engines capable of accelerating particles to near-light speed, and they all contribute to the cosmic ray flux we see at Earth. The closest and most familiar source is our own sun. During solar flares and coronal mass ejections, the sun spews out a torrent of lower-energy cosmic rays. These solar energetic particles can reach Earth in just a few hours, and are a major source of radiation concern for astronauts and satellites in Earth's orbit. They are the local weather in our cosmic neighborhood. However, the most energetic and mysterious cosmic rays come from far beyond our solar system. These are known as galactic cosmic rays. The most likely culprits are the shock waves from supernovae. When a massive star runs out of fuel, it collapses and then explodes in a cataclysmic blast that can outshine an entire galaxy. The expanding shockwave acts like a cosmic particle accelerator, ping-ponging charged particles back and forth and boosting them to incredible energies over thousands of years. We are seeing the echoes of these stellar deaths, which occurred millions of years ago in our Milky Way. Moving up the energy scale, we find even more extreme sources. At the heart of many galaxies, including our own, lie supermassive black holes. As matter, gas, dust, and even entire stars gets pulled in, it forms a superheated accretion disk. The intense magnetic fields act like a colossal cosmic slingshot, grabbing particles and flinging them out in powerful jets at nearly the speed of light. These active galactic nuclei and quasars are among the most luminous objects in the universe and are thought to produce some of the highest energy cosmic rays. But the story doesn't end there. The very highest energy cosmic rays may have origins even more distant and exotic, outside our galaxy, from powerful radio galaxies, from gamma-ray bursts. Other ideas point to the decay of hypothetical superheavy dark matter particles or topological defects left over from the Big Bang. Identifying the sources of these ultra-high energy cosmic rays is a top priority in modern astrophysics. They hold the keys to understanding the most extreme physics in the cosmos. The journey of a cosmic ray is not a straight line. From the moment it is born until it reaches our atmosphere, its path is twisted and turned by the magnetic fields that permeate the universe. Galactic magnetic fields, though incredibly weak, stretch over thousands of light years. A cosmic ray, traveling through this magnetic web, is constantly deflected, its path scrambled into a random walk. By the time it arrives at Earth, it is coming from a direction that has almost no relation to its original source. This is why it's so difficult to do cosmic ray astronomy. It's like trying to figure out where rain came from in a hurricane. Magnetic fields. This magnetic scrambling effect is a major frustration for astronomers. Imagine trying to find a distant supernova by catching the protons it threw out. Because their paths are bent, they all arrive from different directions, smearing out the signal and making it impossible to pinpoint the source on the sky. Only the most ludicrously high-energy cosmic rays, those with so much momentum that even galactic magnetic fields can barely nudge them, travel in something resembling a straight line. For all the others, their arrival direction is a cosmic lie, hiding their true birthplace. Earth's own magnetic field provides a final layer of deflection, steering lower-energy particles toward the poles, which is why auroras are typically seen in polar regions. Solar modulation. There's another major influence on the number of cosmic rays reaching Earth: our Sun. The Sun constantly emits a stream of charged particles called the solar wind. This wind creates a giant magnetic bubble around our solar system called the heliosphere. This bubble acts as a partial shield, deflecting many of the lower-energy galactic cosmic rays that are trying to get in. This effect is known as solar modulation. The strength of the shield is not constant, it waxes and wanes with the Sun's 11-year activity cycle. When the Sun is active, solar maximum, the solar wind is strong and gusty, pushing more galactic cosmic rays away. Conversely, during solar minimum, when the Sun is quiet, the solar wind weakens. The heliosphere's shield becomes less effective, allowing more galactic cosmic rays to penetrate into the inner solar system and reach Earth. This creates an inverse relationship. More solar activity means fewer galactic cosmic rays at Earth, and less solar activity means more. Scientists monitor this cycle closely, as it affects the radiation environment for satellites and future interplanetary missions. It's a cosmic tug-of-war, with the Sun's breath pushing out against the constant rain of particles from the wider galaxy. Since we can't see cosmic rays directly, how do we study them? Well, scientists have developed ingenious methods to catch these ghostly particles, or, more often, the debris they leave behind. One of the most common methods involves detecting the muons that survive the journey through the atmosphere. A simple muon detector can be built using scintillator plates. These are special materials that emit a tiny flash of light when a charged particle, like a muon, passes through them. By placing sensitive light detectors next to these plates, we can record each time a muon zips through, effectively making the invisible visible. Larger experiments use arrays of detectors spread out over vast areas. When a high-energy cosmic ray creates an extensive air shower, the shower front rains down particles over several square kilometers. By placing detectors far apart, scientists can record the arrival time of particles at each location. From this timing information, they can reconstruct the direction the original cosmic ray came from and estimate its energy. The more particles detected, and the wider their spread, the more powerful the initial cosmic ray must have been. These observatories, like the Pierre Auger Observatory in Argentina, are like giant electronic eyes staring up at the sky. Another clever technique involves using large tanks of ultra-pure water. When a particle from an airshower travels through water faster than the speed of light in water, it produces a faint blue glow called Cherenkov radiation. This is like a sonic boom, but for light. By lining the tanks with extremely sensitive photodetectors, experiments like the High-Altitude Water Cherenkov Observatory can map out the light patterns and reconstruct the properties of the cosmic rays that cause them. These water tanks turn a quiet mountaintop into a vibrant cosmic ray detector. Excitingly, you don't have to be a professional physicist with $1 billion budget to participate. Citizen science projects like HISPARC, the high school project on astrophysics research with cosmics, allow schools and universities to set up their own cosmic ray detectors. These detectors are connected via the internet, forming a huge distributed network. When a very high-energy shower occurs, multiple stations can detect it simultaneously. This allows students to collect real scientific data, learn about particle physics, and contribute to our understanding of the cosmos. It's a brilliant way to engage the next generation of scientists and prove that discovery is not just for the experts. While most cosmic rays are relatively low energy, a very small number are accelerated to truly mind-bending energies. The most energetic cosmic ray ever detected, observed in 1991 at the Universities of Utah Fly's Eye experiment, was so powerful that the scientists who found it could only exclaim, "Oh my God!" This single subatomic particle, likely a proton, was traveling at 99.999999999999999% the speed of light. It carried the kinetic energy of a 90-kilometer-per-hour baseball concentrated into a single, infinitesimal point. This is an energy level far beyond anything we could ever hope to achieve in our most powerful particle accelerators on Earth, like the Large Hadron Collider. Particles like the Oh My God particle are extraordinarily rare. An event of this magnitude might strike a given square kilometer of Earth's atmosphere only once per century. Their existence poses a major puzzle for astrophysics. What kind of cosmic engine could possibly accelerate a particle to such an insane velocity? The usual suspects like standard supernovae just don't have enough power. This points toward the most extreme phenomena in the universe, the jets of supermassive black holes and active galactic nuclei, or perhaps even more exotic undiscovered physics. These ultra-high-energy cosmic rays are messengers from the most violent corners of the cosmos. Because of their immense energy and momentum, the paths of these ultra-high-energy particles are not easily bent by galactic magnetic fields. They travel in nearly straight lines, which means in principle we could trace them back to their source. This makes them the holy grail for cosmic ray astronomers. By mapping the arrival directions of these particles on the sky, we can begin to create a picture of the high-energy universe and identify the specific galaxies or objects that are acting as these colossal accelerators. The journey of these particles is as epic as their energy, tens to hundreds of millions of years. Over these vast distances, they interact with the faint bath of microwave radiation left over from the Big Bang. These interactions should sap their energy, imposing a theoretical maximum distance they can travel. This is known as the GZK cutoff. The fact that we detect particles at or near this energy limit provides a crucial test of our understanding of particle physics and cosmology. Each one that we detect is a precious clue, a survivor of an impossibly long and arduous journey across intergalactic space. Radiation is a part of our natural environment. We receive small doses from radioactive elements in the ground, in the air we breathe, and even in the food we eat. Cosmic rays contribute to this natural background radiation. However, here on the surface of the Earth, we are well protected. The atmosphere acts as a thick shield, absorbing the vast majority of primary cosmic rays and the particle showers they create. Our planet's magnetic field provides another layer of defense, deflecting many of the lower energy particles away from us. Thanks to this dual protection, the dose we receive from cosmic rays at sea level is quite small. However, your exposure to cosmic radiation changes depending on where you are. If you take a long-haul flight, you are flying at an altitude of about 10 to 12 kilometers, much closer to where the particle showers are most intense. The thinner atmosphere above you offers less protection. As a result, the radiation dose on a transatlantic flight is significantly higher than on the ground. Airline crews who spend thousands of hours at high altitudes are classified as radiation workers for this very reason, and their exposure is carefully monitored. Similarly, people living at high altitudes, in cities like Denver or La Paz, receive a slightly higher annual dose of cosmic radiation than people at sea level. This becomes a critical issue when we talk about space travel. Once you leave the protective cocoon of Earth's atmosphere and magnetic field, you are fully exposed to the harsh reality of both solar and galactic cosmic rays. The Radiation Assessment Detector, RAD, instrument on the Mars rover. Curiosity measured the radiation environment during its 253-day journey to Mars in 2011 to 2012. The data was sobering. A round-trip mission to Mars would expose an astronaut to a radiation dose that is close to the entire lifetime limit recommended for astronauts in low Earth orbit. This is a major hurdle for human exploration of the solar system. The primary danger in deep space comes from the heavy nuclei in galactic cosmic rays. Unlike the X-rays or gamma rays used in medical imaging, which are like tiny bullets, these heavy nuclei are more like cannonballs. When one of these particles, like an iron nucleus, passes through human tissue, it leaves a dense track of damage, breaking DNA strands and damaging cells in ways that are difficult for the body to repair. Designing effective shielding and medical countermeasures against this type of radiation is one of the most significant challenges that NASA and other space agencies must solve before we can safely send humans on long-duration missions to Mars and beyond. The impact of cosmic rays extends beyond human health. It's a persistent threat to the technology we rely on every day. In space, satellites are constantly bombarded by energetic particles. When a high-energy cosmic ray passes through a sensitive microchip, it can deposit enough charge to flip a digital bit from a 0 to a 1, or vice versa. This is called a single-event upset or a bit flip. While a single bit flip in your laptop's memory might be harmless, in a satellite's flight control computer or a spacecraft's navigation system, it could lead to data corruption, system crashes, or even catastrophic failure. Engineers use radiation-hardened electronics and redundancy, 3 processors voting, to keep systems reliable. For astronauts, the risks are more personal and profound. Beyond long-term cancer risk, studies suggest heavy ion radiation can impair cognitive function. Astronauts have reported seeing flashes of light, likely cosmic rays, passing through their retinas. Even here on Earth, cosmic rays can cause a small but measurable rate of errors in high-reliability systems, from network servers to medical equipment and aviation control systems, due to muons and neutrons from air showers. The universe, it seems, always finds a way to make its presence known. In short, cosmic rays are tiny, powerful messengers from the most violent events in the universe. They come from our sun, from exploding stars, and black holes millions of light years away. They smash into our atmosphere, creating showers of secondary particles like muons that rain down upon us. By studying them, we learn about fundamental physics, the life and death of stars, and the hazards of space travel. They are a constant, invisible connection to the grandeur and violence of the cosmos. Subscribe for such best knowledge bites.